Welcome back to class number 12, Thermodynamics. We are now proceeding on to the section 3.13, the transient process. This is one of the last sections that I'm going to cover. We're going to do some more examples for the rest of this class, for class 12. But I do want to bring up the transient process because we so often will be looking at steady state processes, and steady state processes doesn't mean that it's like stagnant. It just means that if you came back, if you look at a particular parameter and then you turn your head away and then you look back, it's going to be the same parameter, right? So it's going to be the same pressure and temperature, and the state values will be the same as it's moving along. Sometimes we might mistakenly call that equilibrium, but we don't really mean equilibrium in a static sense. Just that things are always the same from any given time or another. An example of a non-steady state is, well, I don't know, like if you were to see a turbulent creek, right, or whitewater rapids, right? Like it's going to be different every time you look at it. It's always in this transient mode. Or if you were like pouring out a bottle of soda, it would be kind of steady state for a while if you poured it just right, but eventually it would stop, right? So a lot of times when we're looking at a transient process, we're going to turn it into a differential equation or an integral or derivative, and try to see something with respect to time, right? So an example that we might have for a transient is to find how temperature varies as a function of time. And then look for what the period of it is, right? What the transient period of it is, kind of like, when does the thing end? And we will find how fast a given mass maybe can adjust to an external temperature. So this is a heat transfer example, and you'll probably cover this topic again in heat transfer. So be on the lookout for it in a year or two when you take that course. I know, but so some assumptions that we always have to kind of make assumptions to make the problems simple enough so that we can solve them. Overly complicated problems so just make us feel bad about ourselves. So we're going to assume that this mass has a uniform temperature. That we can lower, and we lower the thing into a bath of water with a temperature of T infinite. And that's a lot of times we'll just say, well, it's such a large thing of water, it'll stay that temperature. So that's what we mean by the T infinite. A lot of times that we'll treat like the outside or the ocean or whatever. It's like we're not going to raise the temperature of the ocean. And we're going to say the kinetic energy and potential energy are neglected, and that there's no work involved. And we'll also define this theta as being our temperature, or the temperature of the thing, which can vary, and we'll subtract out what the temperature of the big large thing is, and of course the large thing is a lower temperature. And then we also will take a C subscript Q as this heat transfer coefficient, right? So it could be probably conductive or convective, doesn't matter, or assembled together. So here you go. Here's the first law on the left-hand side, or something like it, something like the first law right here. So for the energy of a control volume, and we want to take the derivative of it with respect to time. And so that's going to be the internal energy, and we're going to, so we say this U can be found from the mass times this right here, right? But we're going to take the derivative with respect to time, and the only thing that's going to change is the temperature. So we have that dt, d capital T, d lowercase t, right? Temperature change with respect to time. And because there's no work involved, that's all going to be heat transfer, right? So what we have written right here is the same thing as this. Whoops, I think this is going to be in the way. And what I'm going to do here in a second. So let me erase this right here. What we've written is basically the first law as we've been writing it. I'll write it up here. U2 minus U1 is equal to Q12 minus work 12. Except we took the time derivative of it, right? We said, how much is it going to change over time? So that's what this is. You know, this is the difference right here, and it's per time. And we also said, well, work, there's no work involved. So we said that's the change in temperature of the thing. It's going to be this. No, well, now we also said, well, we have some equations for heat transfer that look like this right here. All right, so we're going to say this guy right here is equal to this guy right there. And we this, remember, we said was equal to theta. So we changed this over here into theta, well, right? So we've just changed these terms into theta, and they just mean the change in temperature. So if we were to go ahead and integrate this, right, with respect to time, we would note that we get theta, the natural log of theta over theta, right? That's just, we're used to that integral, so we skipped a step or two. No, we just really just skipped it. What we did is we multiplied that right there over to this side, and we took this and we divided over here, right? And so when we integrated this theta, it was d theta over theta. We also moved this the constants over to one side, and then we integrated, and we saw that we had this arrangement right here. And based on this, what we could do is we could take the E of both sides of this, and we could also assemble a thing we call the period, right? The period of this right here. And that's going to be a collection of constants. So this is going to be like a time constant. Yeah, that's what we're going to call this. So we call this a time constant. And that time constant is mostly based on the mass of the thing, how well, you know, the specific heat, like how well it absorbs, or how much it takes for the thing to rise up in temperature. It's also the amount of these values right here, which we've turned into R. We're just using this and thinking this is its resistance to heat transfer, right? This is like the heat transfer mechanism right there. So what we're able to do is find for this transient process, this is the way to define in sort of this non-dimensional value right here. And we could see for various time constants how quickly or slowly, here's a quick transition right here, and here's a slow transition of heat will occur. And so this is the transient process. And the example that follows doesn't really use what is really being told right here. Something I forgot to mention, this is called the thermal time constant. I forgot to write that down. You know, it's right there. Thermal time constant. But the next example doesn't really use this these concepts. And the reason why I decided to include them was because I know that you will be taking heat transfer sometime in the future, and it's always good to be exposed to something a little bit, and then at an earlier time, and then later on dive down further into it. So maybe perhaps you will recall some of this when it comes up again in that class.